Welcome to 5-4. We're almost there. We have one more section and one more chapter. So I told you before that we were going to look at integrals and eventually have the limits of integration. So the B to A sort or A to B sort of thing. Now we're dealing with that. And honestly, it's one extra step. And that step, all things considered, is fairly easy. Compared to the integration, this is just plug the stuff in, get an answer. So I don't often say it's easy because that's relative, but what's easy to me might not be easy to you, etc. But in this case, the plug-in step really is easy. It's straightforward. So we are measuring the area under a curve. So I have a little function here. I didn't write it down. This is f of x. And I want to figure out the area between A and B. I integrate and then plug in my limits of integration. I plug in B minus A. Pretty straightforward. The theory of how we get there is interesting, but I view it as beyond the scope of this class. We're dealing with more practical parts of calculus, not the theory of how we get there. But it's a matter of breaking up the region into smaller and smaller regions, getting triangles, as the distance goes to 0, what happens. Interesting. We don't need it to be able to solve our problems. So I really just have some examples with this, and then the fundamental theorem of calculus, which is kind of what we're doing already. So let's say we have a line to x, which I have drawn over here to the right. We want the area underneath that line, and the area underneath goes to the x-axis. So we can clearly see that this is a triangle. Area of that, there we go, is 1/2 base times the height. So we know the area. My base is 2. My height is 4. Should give us 4. Right? 1/2 base times height. Yeah. If we're going from 0 to 2, sorry. So that's what we should get. Well, let's integrate and find out. So the integral of 2x, the antiderivative, is x squared. And then we use this little line, 0, 2. Now you'll notice I didn't write the c. And let me finish this problem, then I'll show you why. So at this point, once we take the antiderivative, we plug in our high value, our top value, minus, plug in our low value, which gives me 4. Yay, it agrees. So that works out nicely. The reason we don't use the plus c, say we did, what do we get? 2 squared is 4 plus c minus 0 plus c. Oh, hey, they cancel off. So the extra constant really doesn't matter for our sakes here because it's going to cancel itself off. So we don't need to worry about it. Okay. Fundamental theorem of calculus. Hey, we just did it. If we have f, a non-negative and continuous function on a closed interval a to b, which most of the time it's going to be, then if we take the integral of f of x from a to b, it's the antiderivative of the function, plug in b, minus antiderivative, plug in a. Like I said, pretty straightforward, all things considered. The biggest piece to remember is your top value, your number that's farther to the right gets plugged in first. If not, you're going to get negative numbers where you should get positive. Now, this theorem deals with a positive function. It doesn't have to be. Interesting things happen when we have functions that are below the x-axis. And next section, we'll look at 2 different curves. So some of our stuff can be above and below. Interesting things happen there. Some properties. Can I fit them all on one screen? I can. So A, B, C, and K are all real numbers. The first 2 properties should be familiar. They're almost identical to what we had when we talked about the beginning of integrals. we just plug in the limits of integration. The second, no, wait, I can count. The third and the fifth one are interesting. The third one is if we're going from A to B and we want to break it up in the middle. So at some C, we can just say A to C, C to B. And we will see a case where we have to do that. This section or next, I can't remember. If we're going from something to itself, the area is 0 because plug in A minus plug in A, you get nothing. And the last piece that's interesting, so my last pink star, if we're going from A to B and we switch the limits of integration, so we go from B to A, that's going to make our function negative. So we're not going to worry about that too much, but just know that it's a thing we can deal with, we can do. Okay. So let's do it. Okay, at this point, I'm going to use fewer U subs when it's the more straightforward ones. As always, if you need to do that, stop, go off to the side, do a U sub, and then kind of catch back up to where we are. I'm just trying to save a little time with this. So I integrate my inside function. I get 1/3 x to the third, x to the 3 minus x. And we go from 1 to 2. Okay. So I like to use big brackets sometimes. Minus, plug in 1. Cool. And this gives me, did I leave myself lots of space? No, I left myself some space. 1/3 times 8. Let's just use it as 8/3. Minus 2 minus 1/3 plus 1. Calculator, I could do this in my head, but I'm not too. Minus 2 minus 1/3 plus 1. 4/3. So yeah, final answer on that. Right? Did I write it down in my calculator right? Okay. Pretty straightforward. Okay. So we can do a U sub. We can expand our fraction. I'm going to be weird and expand my fraction. Not my fraction, my binomial. All right, this gives me 16t squared plus 8t plus 1 dt, right? Add 1, so 16 thirds t cubed plus 4t squared plus t from 0 to 1. Yep, just double checking my math. Okay, plug it in. I get 16 thirds times 1 cubed plus 4 times 1 squared plus 1. And if I plug in 0, I just get 0. Because every term has a t in it, every term's going to 0. So this just gives me 16 thirds plus 5. I get 31 thirds. Yep. Okay. Let's move you up a touch. Same thing. First thing I'm going to do is rewrite. So more than anything, this section is just practicing writing your integrals. Squared. What do I have next? Oh yeah, that's a fun one. Okay. So -3 times add 1 to that will give me 3/2. So a 2/3 comes out front. clean it up a touch, I get negative 2x to the 3/2, going from 1 to 4. Now I'm going to do something a little different. 3/2 is saying root to the 3rd. So that's going to make my math of this a little simpler. Minus negative 2 square root 1 to the 3rd. All right, square root of 4 is 2. So negative 2 times 2 to the 3rd plus 2, because square root of 1 is 1, 1 to the 3rd is 1. And this gives me 2 to the 3rd is 8 times negative 2 is negative 16 plus 2, which equals negative 14, or I really, really hope so. Yeah, I don't see anything that went. Okay. So we get negative 14. We can get negatives. This means that our function is going to be below the x-axis. That is really ugly, but you get the idea. So our function is downstairs. What's happened? Okay, is this my last problem? One more topic after this. So we haven't used that. I think it was the 3rd or the 4th rule, where we break our integral up. In this case, we're going to. So I've already pre-graphed my function. We go from 0 to 2, and it's an absolute value. So our absolute values are more like piecewise functions. So 2x minus 1 from did not leave myself much space. That's a 1/2 over to the side. So at 1/2, we change functions. So we change what we're doing. How I'm going to break this up. So from 0 to 1/2, I'm using this bottom function. So 0 to 1/2, negative 2 plus 1 dx plus, now from 1/2 to 2, I use the positive of the function. So 2x minus 1 dx. And I really did not leave myself enough space. Okay. Pretty straightforward integrals from here. Just be careful. Okay, so I get negative x squared plus 1, and my limits go from 0 to 1/2, plus, let's parenthesis that, x squared minus 1 1/2 to 2. Okay, plug this in. Negative 1/2 squared. That should not be a plus 1. Those should be plus x's. Hopefully you caught that. Plus. Okay, now I plug in 2, so 2 squared minus 2 minus 1/2 squared plus 1/2. And I am going to let my calculator do the work. I get 5/2. I'll double check. that seems accurate. So absolute value functions are ones where we're going to break up our integral. Makes it a little easier to deal with. Actually, I don't know another way we could deal with this unless we're making triangles. All right, last thing, I'm not really going to do any examples of this because it's honestly the same as what we've been doing, just our average value. You multiply your integral from b to a times 1 over b minus a. So you're finding the average value your function takes on over this area or this span. So if you have any problems with that, just throw the 1 minus b over a out front and you should be good with that. All right, that is the end of this section. Pretty straightforward as these go. It's one extra step. The hardest part is sometimes you have to graph them to see what it looks like. If you have a weird function, definitely graph it. Next section, I'm going to bring up some Desmos graphs. So if you don't want to graph these by hand, which I totally understand, it takes a long time, plug them in there to see it. So it'll help you visualize what's going on because visuals are very helpful. All right, I'm going to end it there and see you next section.